In this lecture, let's review the rules for interpreting condensed formulas in organic chemistry, including converting Lewis structures into condensed formulas and vice versa. Before beginning, let's review the common bonding patterns. I'll refer you to my other lectures on common bonding patterns for elements encountered in organic chemistry. I'll give a brief summary here. Neutral carbon will have 4 bonds. These can be 4 single bonds, 2 single bonds and a double bond, or a single bond and a triple bond. Neutral nitrogen will have 3 bonds and a lone pair of electrons. This can be 3 single bonds and a lone pair, a single bond and a double bond and a lone pair, or a triple bond and a lone pair. Neutral oxygen will have 2 bonds and 2 lone pairs of electrons. This can be 2 single bonds and 2 lone pairs, or a double bond and 2 lone pairs. Finally, the halogens, which include fluorine, chlorine, bromine, and iodine, will typically bond only one way, a single bond with the halogen atom having 3 lone pairs. Interestingly, hydrogen, which follows the duet rule, it can only have 2 valence electrons, will also participate in only one single bond, but have 0 lone pairs. Now, let's do some examples. So let's take a look at an aldehyde functional group. Let's convert this condensed formula into a Lewis structure. We'll start from left to right with this first carbon, and this carbon is bonded to 2 hydrogens. This carbon is then bonded to the next carbon in the chain. That carbon is bonded to 1 hydrogen. I'll draw it down here. And this carbon is then bonded to the next carbon in the chain. And before we get to the end, let's take a look at what's happening here and fix this. The common bonding patterns in organic chemistry, these neutral carbons should have 4 bonds or 8 pairs of electrons around it. These carbons have 3 bonds, so we want to give them that extra bond. We can do that by simply just adding that double bond there. If you remember your functional groups from earlier videos, this double bond is carbon-carbon double bond is an alkene. So now the octet rule is satisfied for these 2 carbons. Let's move on to the last carbon, and you'll notice something interesting here. This carbon is bonded to the next atom, hydrogen, and then it's bonded to the next atom, which is the oxygen. You'll notice something interesting, that oxygen does not have another atom on the right side. It doesn't have an atom here to give it that second bond. The common bonding patterns, of course, is that this carbon should have 4 bonds. Neutral oxygen, we've seen before, has 2 bonds and 2 lone pairs. So in this case, we're looking at a double bond there that would give oxygen the 2 bonds, and here are the 2 lone pairs, and this carbon would now have the 4 bonds. So a few things for this example. Number 1, this is the classic carbonyl functional group. And I tell my chemistry students the carbonyl functional group is always part of some bigger functional group. So when you see the carbonyl, you should always look to see what's bonded to that sp2 carbon. On the left side, we have a carbon atom, and this could go on for, some long carbon chain. In this case, it's a 2 carbon chain. The 2 carbons have the double bond So this whole thing here is considered an R group. And on the other side, we have that hydrogen. So when you see this bonding pattern of these atoms, this is called an aldehyde functional group. In this example, let's convert the Lewis structure into a condensed formula. One of the things that stands out here is that we have this bonding pattern of these atoms. A carbonyl, always check to see what's bonded to that sp2 carbon. In this case, we have an R group, and of course on the other side, a hydrogen. So this functional group right here is an aldehyde. So let's draw that condensed formula. So we'll start grouping these atoms. There's a CH3 at the end. This CH3 group is then bonded to the methylene group, CH2. And it's really important how you write the aldehyde functional group. So the next atom in the chain is the carbon, and we have to draw the hydrogen next to the carbon. So this indicates that the hydrogen is bonded to the carbon, and then we'll simply put the oxygen at the end. You have to be careful here. This is important because this hydrogen, if you place it on the right side of the oxygen, then that becomes an alcohol functional group. And we've seen those before. So we saw examples of aldehydes. Now let's look at an example of a ketone. So let's convert this condensed formula into a Lewis structure. We'll go from left to right. Here's the CH3 group. And it's bonded to this next carbon in the chain. This carbon is then bonded to one hydrogen. And in parentheses, we have this group of atoms, the OH group. The parentheses means that this group is bonded to the previous carbon in the chain. So I'll go ahead and draw the OH right here. And so this is the alcohol functional group. We'll continue on with the chain. Here's the CH2 group, followed by this group right here, CO. So notice how this carbon completes the octet for this carbon here. This bond does. So now we have this carbon. Look at the condensed formula carefully. This carbon is then bonded to an oxygen. There are no hydrogens bonded to this carbon. And so you can almost imagine if I continue this chain with oxygen and continue on with the rest of the chain, this carbon is going to be missing some bonds, and we're going to be violating the octet rule. So when you see this classic CO together, that's an indication that this is a carbonyl functional group. And this makes sense. This carbon has the three bonds now, and we can continue the chain, and that will complete the octet for this carbon right here. In the aldehydes, we notice that this carbonyl functional group is then bonded to a hydrogen, but in this case, this chain continues. So here's the methylene group, the CH2, and then we'll close the octet here on this carbon with this chlorine, which is the halide, and so this is an alkyl halide. So here's the carbonyl group again, and as I tell my students, when you see a carbonyl, always check to see what's on either side of that sp2 carbon. So right here, we have a 3-carbon chain. Now, whether it's 3 carbons or 50 carbons, whenever you see a carbon here, we'll go ahead and call that an R group, and I'll call that R prime. And then on the other side, aldehydes would have a hydrogen, but here we have another carbon atom. Now this carbon atom goes to a chlorine. We'll call that R double prime. So the whole point here is that this carbon is in the middle of 2 other carbon chains, whatever they are. But when you see this bonding pattern of atoms, this is called a ketone functional group. Let's go ahead and convert this Lewis structure into the condensed formula. In this example here, we notice this carbonyl again, and we notice that on either side of the carbon atom, we have these R groups. I'll call this R prime. This is a different R group, a different carbon chain. We'll call that double prime. And so when you have that carbonyl bonded to 2 R groups, sometimes they're the same, sometimes they can be different. This is called a ketone functional group. Let's draw the condensed formula. We'll start with the CH3. This CH3 is bonded to this carbon, and this carbon is bonded to an oxygen. It's really important that we draw the oxygen right next to the carbon, and on the other side of the oxygen, we'll draw these other groups, a CH2 and a CH3. It's important to note here that this is not an ether functional group. An ether is when you have an oxygen bonded to 2 carbons. If you follow the rules of bonding, you would realize that the ether group wouldn't make sense here. If this oxygen was bonded to the 2 carbons, look very carefully, this carbon would not have its octet full, thus violate the octet rule. So when you see this CO pattern, that's this carbonyl, and then this R group is bonded to the carbon.